Hello everyone, welcome back to Algebra. Today we're going to talk about the second Sylow theorem. We're going to prove the second Sylow theorem. Just as a reminder, what are the Sylow theorems? There are three Sylow theorems. We're trying to find subgroups. If I have a group G and a prime P that divides the order of the group, and suppose P to the R is the largest order dividing the order of the group, we're trying to find subgroups that play the role of the P primary component in the abelian case, but in the non-abelian case. So the first theorem, the first Sylow theorem, which we have already proved, says that there are such subgroups. There is a subgroup of order, the largest power of P dividing the order of the group. The second Sylow theorem is going to tell me how to find, if I have found one, how to find the others. And what it says is that if I have two, then they are conjugates. There is some G in the group such that H1 is a conjugate of H2. And the third Sylow theorem, which we will talk about in the next video, tells me about how many are there. What's the total number of distinct P-Sylow subgroups? So today we're going to be talking about the second one, the second Sylow theorem. So let me prove that one. Before I start the proof, a reminder that we have proved two preliminary lemmas in the previous video. We talked about normalizer subgroups, and we proved two things. We proved this lemma: if P is a Sylow, is a P-Sylow subgroup of G, and we have some element whose order is a power of P, and that normalizes P, so that after conjugation I get P back, then that element is already in P. And the second lemma that we proved is the following. I have two subgroups, H and K, and I let S be the H conjugates of K. So conjugates of K, but only with elements in H. Then the number of such conjugates, how many different elements are there in here, is given by this formula, by the index in H of the intersection of H with the normalizer of K in G. Where this is the formula or the definition of a normalizer. So let's use these two to prove the second Sylow theorem. So here's the statement that we want to prove, and I'm going to start with P1, but let's just start with P Sylow P. Let P be a P Sylow subgroup of G. And with G, like in the statement, G has size P to the R times M. P does not divide M, so P to the R is the largest power of P that divides the order of the group. And so the order of P is P to the R. Great. Now I'm going to let S be all the conjugates of the subgroup P. So P is going to be P1, P2, up to Pk, be the conjugates, the distinct conjugates of P in G. Great. By the lemma, by the second lemma here, I did not mean to erase things. I wanted the laser. So by the lemma, I know what that is. I know how many there are supposed to be. So by lemma 2, it tells me that K, which is the number of G conjugates, this is the number of G conjugates of P, it has to be given by G and the intersection of the normalizer of P and G. But notice that the normalizer of P in G is a subgroup of G, so this intersection itself is the normalizer. So it's the index of the normalizer. Okay, and well, by I know what the order of the group is P to the R times M, but now by Lagrange's theorem, let me write here, by Lagrange, I know that the normalizer is a subgroup. So this is the order of the subgroup times the index of the subgroup. And that is the normalizer. Let me drop the subscript G, is just a normalizer, the size of the normalizer times K, the number of conjugates of P in G. Let me write that down again in here, that G is the size of the normalizer times K, the number of conjugates of P in G. Now, notice that P to the R is the largest power. This double bar means the largest power dividing the order of the group. And also note that P is contained in the normalizer of P, because remember, the normalizer are those elements of G that when you conjugate G, P, G inverse, you get P back. But definitely, if you conjugate by an element of P itself, you will get P back. And well, the size of P is P to the R, and P is a subgroup of the normalizer. That implies that P to the R also divides the order of the normalizer. But since the order of the normalizer is, well, in turn, a divisor of the order of the group, what we get is that we have an equality in terms of divisibility, that P to the R is the largest power dividing the order of the normalizer. But then notice that this is divisible by P to the R, this is divisible by P to the R, and therefore P cannot divide K. Okay, if P divided K, then the order of P dividing this side would be P to the R and one more P to the R plus one, but that would contradict the fact that the order of G is divisible only by P to the R. So we have this. This will be important later, that the number of conjugates of P in G, the number of those conjugates is not divisible by P. So we will come back to that in a moment. Now let's look for another conjugate that is perhaps not in here and prove that it has to be in there. Any conjugate of P has to be one of these. So let's pick another one. So now let Q be another P Sylow subgroup in G. We're hoping that Q is a conjugate of P so that it is in S, but I don't know that yet. So let's just pick one. And so I want to show that Q is in S, i.e. Q is a G conjugate of P, but I don't know that. So instead, we're going to do the following trick. Now consider the Q conjugates of each Pi in S. So what is happening here? I have S, which is P, that was P1 and P2, and I don't know, let me write some numbers here, 7 and 8, and dot, 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 and then there is some more P's with some subscripts up to PK. Okay, we know there are K elements in S. And now, so these are the G conjugates of P, right? So there is all the orbit of P under conjugation. Now, if instead of doing G conjugates, I look at Q conjugates, that's going to, if there's an action of Q on S via conjugation, and that's going to give me orbits. Not all of them are going to be in the same orbit now because I'm restricting to Q inside of G. There might be suborbits. So what I'm going to get is some packets like this. All of these are going to be Q conjugates of say P1. These are the Q conjugates of P7. These are the Q conjugates of PK. If one is conjugate to another, the other one is conjugate to itself via Q conjugation. So there's going to be some conjugacy classes, which are the orbits of Q acting on S via conjugation. Okay, so what is the size of each one of those orbits? How many Q conjugates are there of P1, say, or how many Q conjugates are there of P7, say? We have a formula for that. Lemma 2 in our video here tells me that the number of Q conjugates of Pi is given by a formula Q normalizer in G of Pi intersect Q. That is given exactly by that formula. And Lagrange's theorem tells me that, well, the size of Q, this intersection of the normalizer with Q is a subgroup of Q. So it will be the size of that subgroup, whatever that size is, times the index of that subgroup in Q. Okay, but this is P to the R, and therefore the index, the number, oops, not index of index, the index which counts how many conjugates are there in this packet, in each one of those packets, in each one of those orbits, the number of conjugates has to divide P to the R. So it divides P to the R and then implies that that count of how many are there in each class, this has to be a power of P. Now, the number 1 is a power of P, so it's 1 or a true power of P. Let's see what that implies. What this implies is that, remember, I had S and then I had P1, P2, the conjugates of P1, and then, I don't know, P7, PA, the conjugates of P7, and then PI, P plus I plus 1, say conjugates of PI, all the way up to the conjugates of PK. So I had what I was calling packets or orbits under Q conjugation and so on. But what I've just proved is this: each one of those packets of Q conjugates, the size of that is a power of P in each case. Power of P, etc. But that implies that the number of conjugates, the number of elements in S, has to be some power of P plus some power of P plus some power of P plus some power of P. But now remember that P does not divide K. That's the first thing we proved in this proof. And if these were all, so then that implies that this is not zero modulo P, but the only way this is non-zero modulo P is if one of these numbers is not a true power of P, is just the number 1. So this implies that there is some EI which is exactly 0, so that there is one class of Q conjugates has exactly one P Sylow. So let's call that one PJ. Let that class be, or that orbit under Q conjugation, let that class be, say, some PJ. Then what happens? Then PJ is on its own under Q conjugation. And what that means is that for every X in Q, we have that when I conjugate that PJ, I get PJ back. But notice that I have that. I also have that the size of Q is P to the R because Q itself was a P Sylow. And that tells me that the size of X is a power of P. But these two things are exactly what lemma 1 we proved in the previous video tells us that under those circumstances, X itself has to be in Pj. The only X's that are of order of power of P that normalize Pj are already in Pj. So X is in Pj, but this is for all X in Q. So that means that every X in Q is in Pj. So that tells me that Q itself is in Pj, all of it. And they are both P Sylows. The size of Q is the size of Pj is P to the R, but if they are of the same size and there is an inclusion, now those two things together tell me that Q has to be exactly Pj, but that was in S, and thus Q is a conjugate of P, and therefore all P Sylow subgroups are conjugates, like we wanted to show to prove the second Sylow theorem. Okay, so that is the proof of the second Sylow theorem. We've seen in previous videos examples of P Sylows and how they are indeed conjugate. So you can go back to those videos to find examples. And in the next video, we are going to prove the third Sylow theorem, and we'll see that it's sort of like very similar technique of finding some sort of like conjugacy classes that is going to give me what I want. So we will do that in the next video.